All right. My name is Eric Prast. I'm the VP of Product Engineering with Examer. I'd like to thank David Brenner and the other 222 Mafia for really setting up this remarkable event. It's fantastic. Tonight I'd like to take a few minutes and talk to you about the exciting work our team is doing to develop miniature, highly integrated Far-UVC modules and how they can be used to revolutionize PPE. So since the pandemic, society has become acutely aware that biological threats represent an ongoing challenge. The rapid development of vaccines and therapeutics have been beneficial, but these are really a reactive mechanism, not a preventive mechanism. So we're still relying on PPE as the main first line of defense, even though it has not had major technological advantages or improvements in decades. So based on this, we have a unique opportunity to develop new innovative solutions. So hopefully by now, everyone's very familiar with the updated guidance from ACGIH for the UV exposure for skin and eyes. Just a little bit of background information, obviously with Far-UVC sources, the dominant source today for now is krypton chloride excimer lamps, but the future's bright. So from Ushio and from, from Eden Park in the center. And then obviously we heard over the last couple of presenters, some amazing research and development that's been done on Far-UVC LEDs. And just as demand grows for this and the research continues, we should see these characteristics improve. So it's very exciting. So throughout the pandemic, we saw a huge variety of face masks. And comparing each of these technologies, we can see that they have a number of key deficiencies. For example, the N95 mask, which uses mechanical filtration to filter 95% of 0.3 micron particles and smaller or larger. And also other masks have reduced efficiencies based upon their manufacturing, their cloth and materials. But N95 masks also restrict breathing and verbal communication and are very uncomfortable to wear for long periods of time. And we can see that all masks use mechanical filtration as a means of protection, which traps live virus particles in the mask, making them difficult to reuse and really reserving them for single-use applications. It was estimated that throughout the pandemic, there was 7,200 tons of medical waste per day, and most of that was due to disposable facial coverings. So really based upon this, a next generation mask should use Far-UVC inactivation instead of filtration and actually kill the viruses and bacteria rather than filtering them, and also allowing it to be reusable and adaptable for future threats. And additionally, it should solve a lot of the hindrances or eliminate the hindrances of today's masks. So if we quantify these requirements, we can draw a comparison of 95% filtration to 95% inactivation. It's not exactly the same, but it could be a close guideline. And this would be greater than or equal to 1.3 log. And it would have to be effective against a set of target pathogens, such as SARS-CoV-2 and influenza. And this could also be adapted to different pathogens based upon their disinfection energies. So we can see the 95% inactivation energy for that. So some of our initial experiments we conducted were to build a square quartz channel reactor using krypton chloride excimer lamps mounted along the reactor in pairs at different orientations. We conducted this experiment to test inactivation in a controlled setting and compare the data to computer simulated models in order to confirm the future development of experiments and devices. So initially we conducted fluence rate field measurements throughout the reactor using a specialized probe and calculated the average dose distribution at a fixed flow rate. And then we performed biological experiments using a T1 phage, which has a similar absorbance to SARS as, and it's also safe to use, doesn't require specialized containment conditions. So based upon this, we administered this aerosolized surrogate virus through this reactor and measured inactivation through a bioaerosol sampler. Our results that we received is 1.6 log, or 97.5% inactivation of T1. And under similar conditions, this would give us 2.8 log, or 99 to 99.98% inactivation of SARS-CoV-2. We can see a picture of this reactor in the lab under a BSL-2 hood. This experiment was performed by Xing Li at Purdue University. So if you have any questions, she actually has a poster number P25. So another problem we had to solve was basically miniaturizing krypton chloride excimer lamps, which are typically quite large and require a lot of room for driver circuits. So along with the partnership with Eden Park, we used one of their lamps that they developed in 12 by 12 millimeter, very small form factor, and deposited a reflective coating behind the lamp to improve its optical performance. And we integrated the lamp and lamp driver as a single monolithic unit. So both the lamp and the lamp driver, and encapsulated the entire device to meet necessary electrical safety standards. And this lamp produces, it uses 1.5 watts, but it could be produced in different form factors based upon the application. So based upon this, we created an initial prototype mask using a miniature microplasma lamp mounted near the chin and an integrated face shield. So we can see some optical ray trace simulations of this mask. We can see that peak irradiance is at the chin and the lips area, and there's a minimal amount of eye exposure still. These simulations were done by my colleague, Christopher Bowers, who's here. He was the one asking all the questions in the front. And finally, we can see what this might look like as a finished product. So just to kind of one of our early concepts. So one of the major challenges that we had to face was balancing the UV disinfection energy or the UV dose with the TLV. By performing CFD analysis to model airflow during inhalation, we observed that particle velocities are the highest in very close proximity to the nose and face. And this just led to very short residence times or very short exposure, which requires a lot of UV, a very high concentration of photons, to be able to develop any sort of disinfection. So this just was a challenge for us to manage the position of the lamp and the power requirements in order to meet that without exceeding the TLV dose. So finally, we created sort of a different concept, which is a curved microplasma lamp that projects outward rather than inward towards the face. And basically, one of the two benefits of this is we were able to use a higher power lamp that wouldn't exceed the TLV. And also we would project a cone of irradiance at an angle where particle velocities are slower, which means we would have a longer exposure and a higher inactivation. So we can see some optical ray trace simulations of this. You can see the projected side profile of this lamp. And you can also see at eye line the radiance field. Peak irradiance is basically at about 100 millimeters in front of the face. And the black area around the eyes showing that eye exposure has been eliminated. We used an optically tuned dielectric film that achieves at least 90% reflectivity at 222. So based upon this, we expect to achieve, hopefully we can achieve 95% inactivation of SARS-CoV-2 under normal breathing conditions, and just being comfortable as well as safe to breathe and easy. Sorry, safe to breathe, easy to breathe, and safe to wear. This is just an ongoing research project we have. So there's still a lot of work to be done, and there's still a lot of conditions we have to solve. A lot of our modeling is, there's other things we have to consider. So next I wanted to highlight our amazing project team that we have, and our partner Eden Park. Special thanks to them, as well as the U.S. Department of Energy for sponsoring this work. We're really looking forward to continuing this research and developing this technology. We recognize we have a lot to still do, but feel like it's a noble goal. Lastly, I'd like to leave you guys with this one thing. But first, is anybody in the audience a fan of Star Trek? All right, good, perfect. Okay, maybe you'll get this. All right. This is Mordok, the benzite. And this is a breathing apparatus he uses to breathe on our planet. And I just like to think of this as a little bit of inspiration of what next generation PPE could look like.
Does anybody have a question?